Hello, everybody. So this morning we have the pleasure of having Andrea Biviano with us to talk to us about clusters of galaxies, of course. I know Andrea since 25 years. He was here for his first postdoc just after his PhD in 93, 94. Then he went to Leiden for a year. First, his PhD was from Trieste, and that's his hometown. Then he came here for 2 years. Then he went to Leiden for a year to work with Peter Katgert on the ENAX cluster survey, one of the first big cluster surveys. Then he went to Madrid for 2 years to work on, what was it, IRAS?
It was ISO.
ISO. IRAS was before that. ISO satellite in infrared. And then he got a permanent position at the Trieste Observatory, where he has been ever since. And he is now, he said, the vicaire, which has nothing religious in Italy, but for us it's something linked to a church. He is also first astronomer. Yes. That, okay. And
first.
whatever that is, first. And so thank you very much for coming.
Thank you. Thank you, Florence. Thank you for being here. It's been 14 years since I gave my last seminar here at IAP. At the time I was in the sous-sol. So now I have this gorgeous amphi, and I hope therefore that I have something new to tell you about clusters of galaxies with respect to what I told you 14 years ago. And as Florence said, I'm going to tell you about structure and dynamics of clusters of galaxies from spectroscopic surveys. And that's the outline of my talk. Basically, I'm going to give a 10 minutes introduction to clusters of galaxies. Some of you might not know what clusters of galaxies are. Probably you all know, but anyway. Then I'll tell you how we determine cluster masses and cluster mass profiles, so it will be a bit of the techniques of how we do that. I'm going to describe our current understanding of cluster mass profiles. And as a consequence of the study of cluster mass profile, you also get as a bonus the orbits of galaxies in clusters, which is related to galaxy evolution. And I'll finish my talk by telling you about what we will do with the Euclid in clusters. Perhaps not everything we will do, but something related to spectroscopy. And I'll using the image of the Louvre to time, to give the sequence of my talk. So we start with the introduction, and hopefully it will be a bit less time consuming than getting into the Louvre. So what are clusters of galaxies? If you read the encyclopedia, it'll tell you clusters of galaxies are clusters of galaxies. There are places where you have a lot of galaxies together, or if you read any paper in the literature, every paper will start with the clusters of galaxies are the largest gravitational bound objects in the universe, and blah, blah, blah. But basically, they are not clusters of galaxies. Galaxies are only a minor part of the cake that compose clusters of galaxies. Most of the baryons are in the diffuse gas, and most of the material we think is something that we call dark matter. And George Abel here was the first to make a catalog of clusters of galaxies it was the first scientific catalog, I would say, of clusters of galaxies that is still in use to these days. One thing you can see in this image, which is interesting, are these big galaxies, which are much larger than the other ones. They are called brightest cluster galaxies, or BCGs. We're going to encounter them later in the talk. In this case, we have two of them in the same cluster, which is the Coma cluster. But generally, you don't only have one. Okay, this is a special cluster. This other guy is my other hero, is Fritz Zwicky. He was the one that in 1933, in his paper written in German, using the virial theorem, essentially calculating the kinetic energy in galaxies orbiting in the Coma cluster, and equating that to the half the potential energy you could get an estimate of what would be the mass to keep this structure together. And it ended up in a mass which was not accounted for by the normal galaxies. So he concluded there should be some kind of dark matter that probably at the time he was thinking about gas or some baryonic thing. And over the years this paper has been looked with some suspicion, and clusters of galaxies have been looked with some suspicions until in the 70s, the rotation curves of galaxies came about, and then people started believing there's something wrong in gravitation, or there's something wrong in our understanding of the components of the universe. And I think that the strongest proof we have now about the existence of this dark matter, that it's probably not baryonic, is the bullet cluster. The bullet cluster is a cluster where essentially what happened is that a group passed through the main cluster, and in doing so, it displaced the gas which was in the gravitational potential of the cluster. So what this paper was pointing out, this is Doug Chloe, is that when you look at the mass in these clusters of galaxies here, the mass is distributed as the galaxies. The mass is traced by a process called gravitational lensing. We're going back to that in a minute. But basically, this blue haze indicates where the mass is. But the purple haze indicates where the gas is. And since most of the baryons are in the gas, it basically is telling you that the matter is not where the baryons are, which is difficult to reconcile with modified gravity theories. Okay, and then going in more detail, once you think that dark matter is indeed the main component of mass in clusters, you may run numerical simulations, which are basically dark matter numerical simulations, and believe the outcome of these simulations, because they're relatively simple simulations. It's just gravity that plays a role. And these three guys, 20 years ago, Navarro, Frank, and White, find out that the cosmological halos of any size, more or less, obey the same kind of distribution in matter. So the mass density profile has this shape, where you see several parameters here, R-2, C delta, M delta, but in fact, C delta is related to R delta, R-2, and R delta is related to M delta. To make the story short, it's a two-parameter function which is able to describe how the mass density changes with radius in cosmological halos. And they also predicted that there should be a relation between these parameters. This is the concentration versus mass. It's the so-called concentration-mass relation, which could also be rephrased into R-2, a scale radius, versus R delta, which is called the virial radius. But anything, the important thing is that if this is the prediction from dark matter only simulation, by looking at this mass density profile in the real world, we can understand something about the properties of dark matter or the way that these clusters actually form. And then clusters also probe galaxy evolution. It was back in the 30s where Hubble and Humason noticed that, or perhaps somebody has noted that even before. But this sentence is from this paper in 31. The predominance of early types is a conspicuous feature of clusters in general. So when Alan Dressel was the one who actually quantified this statement in terms of the fraction of the different population of galaxies, ellipticals, zeros, and spirals. When you go to spirals, when you have a low density, you have a lot of spirals, few F-zeros and ellipticals. When you go to the center, to the very high density environment, which basically are clusters of galaxies, you get a lot of F-zeros and ellipticals, and spirals are no longer there. So there's something happening in clusters of galaxies which make their population of galaxies different from what we have in the field. And then, still about galaxy evolution, one thing we have to understand when you look at this population of different different population of galaxies in clusters is that, first thing, they are not fixed forever. This paper here from Desai, there have been other papers on this subject, show how the fraction of the different types changes with the look-back time or with redshift. Basically showing that when you go to redshift, which is not much far away in time, there were many more spirals and many less zeros. I must say this result is still a bit controversial because it's difficult to distinguish zeros from ellipticals at large distances. But still, it's been confirmed by several people. So it looks like there's something happening in this regime which transforms spirals into zeros. And this instead is from a numerical simulation from Hayes et al. Showing the orbits. So this is a plane of the sky, the virial radius is here, so this is where we usually will look at the cluster here. But if you look at outside, you find all these essentially galaxies which are infalling into the clusters from filaments, big filaments like these, cosmological filaments, and so on and so forth. What is important to understand here is that not only there is evolution with redshift of the population, but there's also the galaxies do not stay. They move around. So it's important also to understand the evolution of the orbits of the galaxies in clusters. And finally, clusters probe cosmology. This is another famous picture from a Nature paper, Borgani and Guzzo, showing essentially that if you are redshift 0, you want to have the same number of clusters. These yellow dots are the clusters in the simulation. In the background, you have the filamentary structure. When you go back in time, you find out that depending on your cosmology, these clusters have to form very rapidly, very recently, or they might be there even at redshift 1.4. So essentially, by chance, this is also shown in this picture where we're showing essentially the mass distribution of clusters compared to two cosmologies. But basically, the idea is that depending on the cosmological parameters, if you want to reproduce the number density of clusters today, if you look back in time, you can understand what's the cosmology, because the clusters would form sooner or later. And so what we have to do is we have to find clusters, a high redshift, and we have also to know their masses to understand what's the mass distribution as a function of redshift, and this will constrain cosmology. So let's now go to the topic of how do we compute these masses. And I'm showing here, this is from Le Louvre, this is Atlas sustaining the world, and of course in this case it's sustaining a cluster. So basically you have three ways to weigh clusters. One way would be to use as I told you, the intercluster gas, which is the most of the baryons are there. It's emitting in X-ray because it's hot. And so what you can do is assume this gas is in hydrostatic equilibrium. And by knowing its luminosity and temperature, you can actually find out which is the gravitational potential that keeps this gas hot and in equilibrium. You need space observations, of course, for that. Or you can use the gravitational lensing. Basically, what happens is that the mass here of the cluster creates a potential well, so the light from the distant galaxies would be deflected by this gravitational potential and would reach us through some deflected trajectories. And so basically, if you look at the shapes or the images of the galaxies in the background of the cluster, you can understand how much these images has been deflected, and therefore you can reconstruct the mass that causes this deflection. And again, it can be done from the ground, but it's much better done from space. What we're going to use in this in seminar is the third technique, which is the same technique basically that I used Fritz Zwicky now 85 years ago. And basically it means that you ask yourself, okay, if you want to have a cluster in equilibrium, all these galaxies moving around, they have velocities, they have position, everything is in projection, but we can, by some technique, understand what's the potential that keeps these galaxies bound together in this system. And for this, you need the spectroscopic observation. So what you want is a lot of observing time and huge collecting area. So you want to go from the ground, basically. Now, how then we use these? Yeah?
Could you just make some comment about compare the three techniques as to which is the best or not?
I think, well, it's the best in which term? For instance, you can talk in economical term, yes, right? Or you can say in accuracy or precision terms. Now, I think the only reasonable thing to do when you have a sufficient observing time is to compare these techniques, because each of these techniques might have its own systematics. Once you beat the statistics, you have to face systematics. And basically, X-ray is less subject to projection effects. We know because it goes with the density square of the electrons. While both lensing and we will see the velocity dispersion are subject to projection effects. But I think by using these different techniques, that the only really good way is to combine them all. But since you know, this is my favorite technique, somebody has to do it, and basically what I'm using is the position and velocities of galaxies to solve what is called the GCLASS equation. The GCLASS equation relates the mass profile of the cluster here to something which is the 3D number density profile. So how many galaxies you have per interval of radius, and to the velocity dispersion profile. This is along the radial direction. So this is from the lectures of Gary. You're an observer here, the center of your cluster is here. This is the projected radius, capital R. This is the 3D distance to the galaxy here, small r. And you have these two components of the velocity, tangential and radial, okay? But what you observe is actually the line of sight component. So the projections of these vectors onto this dashed line, okay? And you have this third term, which is beta. And beta is basically relating how much kinetic energy you have in the tangential component of the orbit with respect to how much kinetic energy you have in the radial component of the orbit. 1 minus these quantities, and it tells you practically how elongated is this velocity ellipsoid, okay? So if this radial vector is much larger, you'll end up in a radial orbit. If this velocity vector is much larger than the other, you end up with a circular orbit. So basically, when beta is greater than 0, you have orbits which resemble like comets in the solar systems. When beta is negative, you have orbits which will look like planets in the solar system. And then the beta equals 0 is called isotropic orbits. Okay, then, but we don't observe the 3D quantities. We observe everything in projection. So basically what we observe is the distance from the cluster center, this capital R, and the velocity along the line of sight, which now, in general, we put this velocity in the rest frame of the cluster. So these are real observations. These are galaxies. Each dot is a galaxy in a cluster, ratio 0.44, showing essentially the characteristic feature of decreasing velocity amplitude as you go out, which is natural expectation if you want the system to be bound. These, if you project along the x direction, x-axis or y-axis, will convert in something like the number density profile in projection, n of r. So how many galaxies you have per beam of radius, basically, or the velocity dispersion profile. So what's the velocity dispersion? What's the amplitude of this vertical scale as a function of distance from the center, okay? So there have been a lot of studies how to solve this problem, because you want to go from the projected quantities to the 3D quantities. I will not enter in detail, but you can ask that perhaps after the seminar if you're interested. But basically what they are going to use here are two techniques. One is a technique which has been developed in this institute, and it's called MAMPOST. And basically what MAMPOST does is assume, take some models for the mass profile and for the beta profile, which I remind you is something of like an orbital profile, to predict what would be the probability of observing a galaxy in a given position of this projected phase space. And essentially, by making a maximum likelihood analysis, you constrain the parameters of these two models. On the other hand, you can also solve the Jeans equation by knowing already one of the components that you want to determine. If you know, for instance, the mass profile, and you can know that from lensing or from X-ray, then you can use the two observables, these two projected profiles, to constrain beta R, to constrain the orbits. This is also a work that's been done originally by Gary here with James Binney. It's been, I'm using the development of the same technique by Solana and Salvador Soler. Now we're going talking business. So what's the spectroscopic data sets we have? Basically we have, I'm using a low redshift data set which is called WINGS, OmegaWINGS. PI is Fasano, Husnai Retard, and Bianca Poggianti. Going to higher redshift, I'm using the CLASH-VLT data set, where the PI is Piero Rosati and Mario Nonino. This is also, this is basically VLT, VMOS observations, but now we're getting data with MUSE. And then going to higher redshift, there is this cluster sample from the South Pole Telescope, Sunay Zeldovich selected clusters, which has been followed up with many telescopes to get the spectra. And finally, I'm using this Gemini cluster astrophysics spectroscopic survey. And as you see, the number of members, it's 9,000 in 68 clusters here. There you go to same number, but in less clusters, so you have more galaxies per cluster. You're going to 3,000, but in 110 clusters. So you see what we're going to do next is, in some cases, we're going to have to stack these data sets, because only for some of them we will be able to constrain the parameters cluster by cluster. And so on and so forth. Of course, when you go to redshift 1, you don't have many members. And now we're going to talk about cluster mass profile. And I noticed that NFW fits very well this statue that you might have seen before. So probably that only just means that NFW is very generic fitting function. But then what we find basically is that when we solve the Jeans equation and we find the mass profile of the clusters, or we generally find that NFW is a good fit. NFW, this model, fits the observations pretty well. This is from a paper in preparation with Gary. I'm actually here also to work with him on, we should submit the paper next week. And basically is low redshift clusters. We find that the inner slope is probably a bit steeper than NFW, but NFW is still acceptable. This is the same data set basically, but now it is a cluster by cluster. What I did, I assumed NFW, and I tried to solve for the concentration mass relation. So basically these two parameters that define the NFW model. One is the amplitude, the mass, and the other is the shape, how concentrated is the mass. And you predict, observation theories predict this pink region here. And what we find is this red line with the huge yellow error bars. And the interesting thing, though, is that previous determination of several using lensing, X-ray, and even dynamics, kinematics, we're getting all kinds of possible slopes and relations, and there have been, for many years, there have been claims of tension with the theoretical predictions, but now in the latest determination tend to agree with this theoretical prediction, and so even kinematics here is in agreement. So NFW seems to be okay, a low redshift. When you go redshift 0.4, in previous case, the mass profile was based on a stack of something like 50 clusters of galaxies. In this case, it's only one cluster of galaxies because we have a lot of spectroscopic member. And it's a cluster redshift 0.44 showing the mass versus radius as the mass profile grows. And this is answering partly Henry's question. What is shown here is strong lensing, weak lensing termination, X-ray here, and kinematics, which is the gray and the green shaded region. And the best fit NFW seems to be very well accommodated by the analysis. If you go to even higher redshift, what I'm showing here is the mass profile determination for a stack of redshift 1 clusters. When you go to redshift 1, it's tough. It's probably, you can't do that with X-ray so far, but probably you can do that even with lensing, but we could do that something with kinematics. And basically this is a concentration versus mass for the stat cluster. This is a theoretical expectation, and these points are, depending on how you do it, it's our result. So again, it seems that NFW is in agreement with observation. So it's becoming boring talk, right? This is, you can ask then, but is NFW the only model that fits the observation? And the answer is no. When you look at this figure, what you see here is the ratio between the mass profile and the mass profile that we get assuming the NFW model. This is for the same cluster I've shown before. And the other lines are basically different models, how they deviate from the NFW prediction. And the shaded region is the 1 sigma uncertainty on the NFW mass determination. And basically you see that all the models, except perhaps this soft and isothermal sphere, which seems to be out here of the error bar, and most of the models, forget about the green, but all the other lines are basically within the uncertainty. So other models cannot be rejected with this data set. So NFW is fine, but what can we do better? To do better, you have to go to the very center of the cluster. You have to go to the constrain the mass, not by the kinematics of the galaxies, but by the kinematics of the stars in the central galaxy of the cluster, which is the BCG I've shown you before. This is showing basically how you can constrain the mass profile by the different techniques. Basically, you show that we can get to something like 100 kiloparsec or perhaps 50 with the galaxy kinematics and distribution of. But then if you go to, well, strong lensing can constrain you up to probably 10 kiloparsec. You want to go inside, you want to have the BCG stellar kinematics. That's shown also here. These are real data. So these are essentially the points are the observations. This is the velocity dispersion profile of galaxies in the potential of the cluster. And this is the stellar velocity dispersion profile of the BCG at the center of the cluster, okay? And the lines here are the best fitting models, which we find by, again, by using MAMPOST, developed in such a way to have a simultaneous constraint that's coming from the motion and distribution of galaxies in the cluster and the motions and distribution of stars in the BCG. And by doing a Monte Carlo Markov chain, that's the result that we get. Basically, I'm showing here something which is called the constraints on the generalized NFW, where the inner slope is now not fixed to 1 as for NFW, but it's free to vary. And the other parameters, you've already seen that. This is scale radius. This is essentially the normalization, R200 of the profile. And what do we see here, without getting into too much detail, is basically that you need the galaxies to constrain R200, so the scale, how massive is the cluster. But you need the BCG to constrain how goes the inner mass profile, what's the slope of the inner mass profile. And when you combine the two probes in green and in blue, you get the red contours, basically, which shows you that you can get a pretty good estimate of the inner slope. And the inner slope we found is 1, okay, with this error bar, so it's fully consistent with NFW. And this is the inner slope of dark matter, because we subtracted the baryonic component, okay? Let me go ahead. So everything is consistent with NFW, but are we happy? What are the predictions of cosmological simulations if we look at that in more detail? I'm considering here two simulations. One is from Eagle, the other is a simulation done here, essentially. And here it's showing the total mass profile inner slope, how you expect it to vary with mass. And according to this simulation, there should be this trend, and other observations are basically in agreement with this trend. And this is our point from the low redshift cluster, the work we're doing with Gary, which is a bit above, but it's still consistent with the prediction. When you go to the dark matter, so you subtract the baryonic component from the total matter, you're left with the dark matter. That's the prediction, which also shown the prediction from the Eagle simulations. These are, and from observation from Newman, for clusters and for groups. And our point is here, the point I've just shown you. So it's around -1, right? So we don't really know if, which is the right answer, because basically we don't know how the simulation would continue in this high mass regime. But there seems to be an indication of a flattening here. So either there is a huge range in the dark matter inner slope for clusters, or either we or Newman have done something wrong. Yeah.
Can you just say something qualitatively about what's the origin of the NFW slope? Where is it coming from? Is it just from the dark matter, or is it dark matter plus gas?
No, I cannot tell you why is -1, but I can tell you what can change the slope, essentially. So the interesting thing here, but I'm going to come back to that in the conclusions basically, is that if you determine the dark matter inner slope for different clusters and you find it to be different from cluster to cluster, you learn something about what's happening at the center of clusters in terms of several processes which could be influencing the dark matter inner slope, which could be dynamical friction, which could essentially transfer energy from the big massive galaxies to the dark matter particles, adiabatic contraction, which is something that has to do with the hydrodynamics, essentially, and AGN feedback as well. AGN feedback can also create something which is different from, make the inner slope less concentrated. So we're learning something about the baryonic processes and interaction with with dark matter. Okay, everything is NFW. Not really. Not all classes are NFW. This is the same relation I've shown you before, but now I'm showing you the real data. There's a huge scatter, okay? It sits around the expected theoretical relation, as I've shown you. But there is this cluster here, for instance, 1631. And this cluster here, which was not in the WINGS sample originally, but I put it here in this relation, which sits at a very low concentration for their masses. So what are they? Well, I looked into detail of this cluster. We get some VMOS observation. And I discovered that basically in the velocity distribution of this cluster is bimodal. So all the evidence is that this cluster is undergoing a merger. This other cluster, I don't have more velocity data than I have here, but there was this paper recently by Babazaki, which showing essentially the intercluster medium entropy is very high, which basically means these are the general shape of this entropy for other cluster, and this is how it goes for this cluster, which corresponds to a low central gas density, basically. So the interesting thing here is to understand what these outliers are. So most classes are NFW, that's fine, but some classes are outliers, and we want to know why they are outliers, basically, because this could have some influence on your cosmology. When you try to constrain cosmology by doing some search for clusters, and you're missing this cluster because they have a low gas concentration, so their X-ray flux is low, you want to know if this is troublesome or not, okay? So let me go now to orbits, and this is the Sitten scribe, of course, with his beautiful eyes that everybody praises. And So let's start with the orbits of galaxies at low redshift. So as I told you, orbits is something that you can get from the Jeans equation as a bonus in a sense, okay? In fact, it was considered to be a degeneracy between the mass profile and the anisotropy profile. But when you break the degeneracy, then you get that as a bonus. And so, of course, to know the orbits of galaxies, you cannot do that with X-ray or lensing. You need spectroscopic observations. This is a low redshift. This is the same sample I've shown you before, the mass profile, which has this slope of 1.6 near the center. The orbits of elliptical and A0 have this essentially distribution around the 1 in this parameter, which is the ratio between the radial and tangential velocity dispersion. Basically, that means that they don't prefer radial orbits over tangential orbits or vice versa. They have isotropic orbits. While spirals have this increasingly radial anisotropy, okay? Which is reminiscent of the fact that they are an infalling population, right? And they tend to infall on mostly radial orbits. So nothing so strange, but why are these orbits isotropic? We don't really know at this moment. This is also consistent with the previous study in another cluster, okay? When you go to higher redshift, and not much higher, redshift 0.44 in this case, what you find here is that this shape of, before we were looking at sigma r over sigma t, here I'm looking at beta. So basically what was 1 before is now 0. But basically you see when you are in this region, you have radially elongated orbits. When you are in this region, you have tangentially elongated orbits. And you see that basically all the galaxies, even when you split here between red and blue, they tend to be on radial orbits, which is not what we see at low redshift. Okay? If you even go to redshift 1, you find the same. So what can be happening? We don't really know. But we're trying to have some guess on what's happening. What is shown here is a paper from Fritz et al. The quenching timescale seems to evolve as the dynamical timescale. Now, the way they calculate the quenching timescale is basically by counting fraction of galaxies of different types at different redshifts, okay? And they ended up with this relation, this green relation here, and they noticed that it's different from what you would expect from molecular gas depletion timescale, which would be flatter here. It's more in line with what you expect from this dashed line, which is the evolution of the dynamical timescale, assuming that you know how the mass accretion of the cluster evolves. So we don't really know what's happening, but we might think of something like a scenario where spiral enter the cluster, they evolve into zeros, they transform very rapidly at high redshift, and so what you're left over are S0 galaxies or even red spirals, which still move on radial orbits because they transform before having time to transform their orbit. When you go to lower redshift, the transformation timescale is longer, and therefore what can happen is that by the time they transform, they also evolve their orbits. But I don't know how this orbit evolution happens. I don't know the mechanism for that. There is this paper which we published recently, Cava, myself, and Gary, which is showing the velocity dispersion profile of the three populations, spirals, S0, and ellipticals, in regular cluster here and irregular cluster here. So if you think of irregular clusters as something which eventually will evolve into a regular cluster after dynamical relaxation, there is an indication here that the S0 population have a kinematic which is intermediate between ellipticals and spirals. While when you go to regular cluster, they're much closer to ellipticals. So whatever's happening here, it seems that as an irregular cluster evolved dynamically into more regular ones, also and as spirals evolve into zeros, also the orbits of these zeros tend to become closer to that of ellipticals. And then we can discuss about the possible mechanism that caused this evolution. This is a recent simulation from the Magneticum Pathfinder simulations from Lotz et al., which is about to be submitted. The good thing is that they find, this is the same cluster shown you before, redshift 0.44. From this simulation, they find that the velocity and isotropy profile, so the orbits of their galaxy in simulation, are the same as we find, or very similar to what we find in our observations, which is reassuring either for them or for us, I don't know. And then they are, of course, able to follow this profile over redshift here, from redshift 1.4 to redshift basically 0.2, and for different clusters of different masses. And there is some indication that blue galaxies have a higher radial anisotropy than red galaxies, but also that there is some mild evolution over time, and orbits tend to become a bit more isotropic with time. The mechanisms that you might think for orbital synchronization are several. It could be two-body relaxation, it could be the normal cluster growth, or the violent cluster growth by mergers, dynamical friction and tidal stripping, and I'm running a bit late, so let me go fast here. Basically, what we're trying to understand is which of these processes can do the job. One problem we face is that this is yet another sample. This is the SPT-SZ survey that I presented in the beginning, showing again these orbits only for passive galaxies here. And you see that from redshift 1 to redshift 0.2, essentially, they keep basically the same shape with huge error bars, okay? But there's no indication of these orbits becoming isotropic. Well, there would be some indication here, but then they become, again, radial here, so I don't know. But basically, this seems to indicate that the evolution is very fast, which is something I don't understand. You cannot evolve the orbits in so fast. There's no reason why they should suddenly evolve from something which is radial to something which is isotropic. So there's some work to be done here. When you split the sample by mass, cluster mass, you can understand something about one of these possible processes for orbital evolution, which is dynamical friction. Dynamical friction is more effective for massive galaxies in low mass systems. So basically, if you have the same population of galaxies, you expect more dynamical friction in the low mass systems. And therefore, if that was the cause for orbital isotropization, you would expect that in the low mass systems, you would see orbits which are more isotropic. And you don't see any difference. So basically, this is split by masses, and the orbits are all the same. So this essentially rules out dynamical friction as a main important process for evolution of orbits. On the other hand, tidal stripping could play a role. This is from a paper of my former student Nunziatella. She's now at Tufts University. It's a pretty complicated plot. So what I'm showing here are still this beta profile, so radial orbits here and tangential orbit in this region, for massive early type galaxies and low mass early type galaxies, okay? And you see that in the external part they show these radial orbits, as we've seen. This is a redshift 0.2, by the way. And on the other hand, when you go in the inner region, it seems that there is a separation of the two. So what could possibly happen in here? One interpretation was that possibly it's tidal stripping doing this game. Suppose you have this galaxy orbiting the center of the cluster center is here. If the galaxy is passing very nearby as a small pericenter, there are tidal effects which are important because the potential of the cluster is very steep. It's NFW, it's CASP, and so some of this material can get stripped. If a lot of material gets stripped, eventually the mass of the galaxy and the luminosity drops below your detection limit. So it exits from the sample. The ones that are left might be the ones which have avoided the center, so they are on more circular motion. So they would, you would end up to have a selection effect in your sample that preferentially identify tangentially elongated orbits. This is also found in the simulations I've shown you before by Marcel Lotz, which works with Klaus Dolag in Munich. When you go even below, it's possible that these galaxies are not completely destroyed. So if you lower your detection limit, you might find these galaxies again at a very low mass. And perhaps that's what we have seen in the coma cluster. This is the anisotropy we have identified for galaxies of 10 to the 7 solar masses, which again goes in the opposite direction. They are very radial. So it's possible that these galaxies, which have been losing mass here, they drops out from the sample here, which stops at 10 to the 9, but they are found again orbiting in their, keeping their radial orbits, but with much lower masses. Okay, let me go to Euclid. I don't know if you know, but there is a Euclid statue outside the Louvre. So if you, and probably, you know, he's been afraid of his terrible eye looking at him. Anyway, so Euclid and clusters, my last 5 minutes. Trying to be fast. I don't have to tell in this place what Euclid is, right? Euclid is France, Italy, many other places, but Euclid peak is here. And of course, we wish all the best to Yannick. And basically, clusters are called the additional cosmological probes in this Euclid survey, okay? So we don't have really the same status as BAO and weak lensing, but we are considered more important than Milky Way nearby objects, say. So there are actually a lot of people working in clusters in Euclid, something like 100 members in the science working group led by Bartlett, Moscardini, and Weller, and other people working in the work packages, which I'm leading together with Sophie Moreau-Gordato in the implementation of algorithms. What I usually say, but I shouldn't say here because I'm recorded, is that the way it goes is we do the job, they verify that we did a good job, and they use our job to make science, okay? But in fact, there's a huge overlap between these teams, so we're basically in all teams. Okay, and the usual joke is that, okay, there are 41 active members, 30 are passive, and 20 are in the Green Valley, okay?
They're in Ireland.
Sorry?
They're in Ireland.
No, Irish people are good workers. Okay, so this is how are we going to detect these clusters? Basically by the photometric survey. You know, well, there's also spectroscopic survey, but what is shown here is adapted from Sartori's. You show the selection function of Euclid. So the mass of the cluster you will be able to detect as a function of the redshift. And the photometric survey, our prediction was an analytical prediction at the time, but it's now confirmed by numerical, we essentially tested several cluster detection algorithms on numerical simulation which were designed to create a mock survey of Euclid. And the end result is shown here for one of these detection algorithms, Amico. This is in terms of completeness, this is in terms of purity. And basically you see that when you go to this level, 10 to the 14 or so, you basically are in the spot where you have a high completeness, high purity, and that's by the photometric survey only. Lensing, unfortunately, it will not be very effective in detecting individual clusters much below, much high redshift, say. And spectroscopy, this is the line of the mass of cluster with at least 5 spectroscopic members. With less than 5 spectroscopic members, you don't really detect the cluster in spectroscopy. So you have to do that with photometry, okay? And there have been a challenge among different detection algorithms. In the end, we have chosen 2, which are pretty different in the way they detect the clusters, because we don't want to be biased on a precise detection technique. If we have time, if Euclid is not sent to space very early, we might eventually think of including other techniques. But for the time being, what we have as manpower is allowing only to consider 2 of them. And then I want to do cosmology with Euclid clusters, and this is a figure from Sartori's showing the parameters of dark energy, how they will be constrained by clusters of galaxies. But basically, the point of this figure, without getting into much detail, is that you need to have a very good characterization of the mass observable relation. as good as possible. You want to know the bias in this relation, the scatter, and the evolution of the bias, the scatter with redshift. So it's tough, but basically it means that you need to calibrate the observable versus masses. How do you do that? Well, you can do that with lensing, and this is again, this is a figure done by Jim Bartlett, basically, showing that when you stack the weak lensing signal around the clusters being detected in the photometric survey, you actually see something. If you want just to do a detection, blind detection, it's hard, but when you look at the stacked signal, you can do something and actually calibrate the mass with a given precision, how to redshift, basically, as you see, 1.4 or so. And of course, you can do something from other survey, like eROSITA, but you know that it will not be very effective when you go beyond the redshift 1. So one idea was, okay, we have a spectroscopic survey in Euclid. This spectroscopic survey will go to essentially detect the H-alpha line for galaxies between redshift 0.9 and redshift 1.8. So that's a regime which is interesting because lensing is becoming in trouble. X-ray has already become problematic. So can we do something in this redshift regime using the spectroscopic survey? There are two problems here. First problem is that basically this is a slitless spectroscopic survey, so you basically have a lot of confusion. That means that you only rely on emission lines, so H-alpha. The other thing, so this excludes already the passive galaxies, which are the most abundant population, at least up to redshift 1. But it might be working very well at high redshift when actually there is there are some indication that clusters around redshift 2 have a lot of star formation, okay? But the other problem is that when you want to know how many spectroscopic members you will have as a function of the mass, I'm not going into detail. This is essentially analytical estimation. This is simulations. But basically, it's around 10 or less than 10 per cluster, which means you have a poor spectroscopic sampling. Even with that, you can do an excellent job in defining the mean redshift of the clusters, which could help a lot in increasing the purity of the sample at high redshift. Okay? What is shown here is basically what you can do. It's a simulation, what you can do with the spectroscopic survey and what you can do with photometric survey in terms of the difference between the true redshift and the observed redshift. Okay? And you really decrease by a factor, almost factor 10, more than factor 10 actually, the uncertainty in the mean redshift of the cluster. So that's fine. Well, there are some catastrophic outliers, when you find 2 peaks in the redshift distribution, which is here, but we can handle that, I think, by combining with the photometric redshift. On the other hand, you want velocity dispersion to get the masses. And after developing a new technique with my postdoc, Biviano Munari, we were able to essentially find unbiased. This is the ratio between the velocity dispersion we observed and the true velocity dispersion. These are all simulations, of course, and as a function of the true velocity dispersion. And you see it's unbiased. This is in logarithm. But the scatter is huge, okay? And what you also see is, the color indicates basically what's the fraction of real members you're detecting. So clearly the darker colors are closer to 0 here. So the spread is caused by the fact that you get the wrong members, basically. And the statistics is shown by the size of the symbol. So we are working on that, basically, but at the time being, it's hard. It's hard to get the RMS to a level that will allow you to do mass calibration. Although, of course, cosmologists will teach me that you don't care, as long as you calibrate the bias and the scatter sufficiently well that you can know how much scatter you have and what's the evolution. I'm a bit late. This is what I'm trying to do now, stacking together these simulated clusters and using MAMPOS to see if I can detect the mass. I'm not going into much detail here, but basically it's promising. R200 seems to be overestimated by 10%, the concentration underestimated by 30%. The velocity anisotropy is okay, but only because I forced all clusters to have the same velocity anisotropy, so it's easy. So this has to become more complicated, but let's say it's work in progress. So there is hope, and the take-home messages come along. I'm sorry, I'm 54 minutes now. So let me just sum up what I said. Basically, cluster mass profiles are consistent with NFW. Essentially, the fact that you find NFW is already established redshift 1, and you don't find any cluster redshift greater than 2, which is well formed, it means that NFW is something which is produced very rapidly, okay? So the obvious process you have in mind is violent relaxation. I haven't got time to talk about these two things, but you can ask if you want. The inner slope, we are trying to constrain that with the BCG. It's important to distinguish total from dark matter, because in the inner part you're dominated by the baryons in the BCG. We want to understand, but this we discussed already, if there is a real cosmic variance. I mean, if different clusters have different dark matter slopes, that would be very interesting, because it will teach us something about the interplay of baryons and dark matter. And orbits, well, we just went through. There seems to be isotropic near the center, more radially elongated outside. When you go to, you see that there's a difference from redshift, say, 0.3 to redshift 0, which we do not understand in the orbits of passive galaxies. We need some process which occur at very low redshift and very rapidly, so it's hard to explain that. And then we essentially excluded dynamical friction as a possible contributor. We have said that tidal stripping can do something in changing the orbits, but we have to still investigate something more. And I think that's my last slide, which is perspectives, which essentially, what are we going to do? Well, we're going to constrain the mass profile in the inner region for clusters of galaxies using Muse observations. Both are redshift 0.4 in individual clusters, basically, because the CLASH-VLT data, in the end, will have something like 10 clusters, each with 500 spectroscopic members. But we can do that also for a stack of low redshift clusters. There's literature data there that one can use, also for the BCG. And the other interesting thing would be to constrain the outer slope of this profile, which I didn't have time to talk about. But basically, according to simulations by Dimmer and Kratsov in particular, the shape of the mass density profile in the outer region is related to the accretion rate of the cluster. So by constraining the shape, you learn about the accretion rate, and so the evolution of clusters. And you can do that in two independent ways, by measuring the shape of the mass density profile, or by measuring the substructures which are around the cluster. This is something we have done in the past with Christophe Adamy, Florence Durret, and the late Alain Mazur. And then, okay, then I want to understand if the orbits are the same for all clusters, or if there is a scatter from cluster to cluster. That could be done by CLASH-VLT. And that's what I just said about Euclid, and I think I'll stop here. Thank you for your attention.
Thank you. Now it's time for question. Gary?
So I shouldn't ask you questions after your beautiful talk, Andrea, because we've talked a lot. But I want to make a comment and answer to Henry, if he's still here. You're still here? And then a question. So Henry asked, what's the origin of the inner slope of the NFW? So there's a nice paper by Avishai Deckel in 2003, which says the following. If you have a very, he made some experiments about this. If you have a very steep slope, steeper than -1, and you have a sub-halo that falls into the halo, it gets tidally stripped before it managed to get to pericenter. So it deposits most of its mass further out, and so it makes a shallower profile than -2. And on the other hand, if you have like a chord profile, then you don't have this tidal stripping, and then the galaxy falls in by dynamical friction and adds its mass to the center. And he said the sweet spot is -1.1.
Okay.
It's a detractor, he says. Okay, so I think that's pretty cute. I mean, you can also talk about violent relaxation and things like that. And then I just had a question, okay, for substructure. So you showed that some low concentration clusters had bimodal velocities, and you can also try to find substructure just from the positions on the sky of the galaxies. For example, in Euclid, we won't have much velocities to look for bimodality, but we'll have the positions. In your opinion, which is more important, the positions or the velocities, if you cannot have both? You know, so will Euclid be able to do a good job, and will it be important or not that Euclid messes up substructure clusters with other clusters when you try to stack them to get some constraints on cosmology?
Okay, I don't know the correct answer, because these are all things that we are working on concerning Euclid. What I can say is that in the past I worked with substructures in velocities, in positions, and the best way to handle substructures is actually to have X-ray observations combined to optical observations. Then you really get the thing right. But if you don't have X-ray observations, then best thing would be to combine velocity and positions.
So we will have.
If you don't have that, what happens is basically that I think that most of the overestimation of mass can be detected in velocity, because basically in position you would see the two objects when they are projected. You know, if that's the plane of the sky, you see the two objects like that, but the velocity vector of the collision is along the plane of the sky. So basically you don't have any component along the line of sight. So basically that doesn't really influence your dynamical mass estimate, which is strongly based on velocity dispersion. On the other hand, if the collision is along your line of sight axis, you will find it hard to detect by position. So you want to have the velocities there. And that's therefore, I think, the most important thing is to detect that in velocity space.
Hello, thank you for the nice talk. My question is, why do you expect dynamical friction to be more effective in low mass system?
Well, it's just the Chandrasekhar formula, which indicates that when you have a massive galaxy, it's a ratio of the mass basically of the galaxy that infall with respect to the If you want to see it physically, what happens is that the massive galaxies will create a wake in its motion of dark matter particles, which is more important when the global mass ratio of the system is higher. But it's basically Chandrasekhar's formula.
Okay. And I have a second question. So when you measure the velocity dispersion of a BCG, aren't you like more subject to measurement errors or things like that? Because to me, it's like trying to measure a really small velocity dispersion compared to a big velocity dispersion when you measure satellites, galaxies in the clusters.
Okay, you've seen the plot, and it's true that in the velocity dispersion of the stars and the BCGs are smaller than the velocity dispersion of galaxies. But on the other hand, the kinematics is really dominated in that region by the BCG potential. So that means that basically there's no problem. You're not mixing the two things. Of course, the BCG has to be at rest at the bottom of the potential of the cluster. So you cannot do that in any cluster. So I was cheating a bit saying we'll have 10 clusters for which we can do the job. We will have 10 clusters for which we will try to do the job, but we already know that one or two of them will not be good for that job because the BCG is offset from the center and this sort of thing, so you cannot really do that.
It's lunchtime as well, so I'll just be really quick. In the galaxy cluster work you're doing in Euclid, have you guys looked a lot at the Euclid deep fields or not?
That's a good question. You're actually asking all these questions because I said that Irish people are good workers, right? Which I really mean. That's something I'm going to do if I have time, even as soon as I'm back to Trieste before the meeting we have in Munich, because it's important. The deep field can really help us in this respect. So yeah, it's something we have in mind. We haven't looked at that yet.
I might have a question actually. So you showed the change in the radial over tangential velocity dispersion, the function of distance. in the observation, it is seen also in the SDSS that the alignment of satellites with respect to the central galaxy changes as a function of distance and changes as a function of the halo mass as well. It's in a complicated fashion, and we see that in simulations. So I was wondering whether you can link this change in position alignment with the kinematics as well.
Okay, I think that that's one of my old dreams, in fact, which I don't think, there's a nice paper by, two nice papers. The latest one I have in mind is that by Radek Wojtak. Basically, the old thing that, one of the main systematics that you have in the determination of the mass of a single cluster is triaxiality. Clusters are not spherical. Everything I've shown you is spherically symmetric. And basically, the velocity vector is elongated along elongated along the same direction as the positions of the dark matter particles or the galaxies. So the idea, in fact, is that it's hard to get the triaxial shape of. There are some people doing that: Mauro Sereno, Andrea Morandi. But it's hard. I have to combine SZ, X lensing observation to find out which is the shape, 3D shape of the cluster. So for the individual cluster, this is difficult to do. But you can probably think of something like statistics, right? So a statistical sample of clusters, and you look at the distribution of galaxies, or even at the shape of the BCG. Because if the BCG is also elongated, like the large-scale structure. This is Michael West in the 80s who told us. And basically, the idea is that if you find the BCG to be circular, it's a good, or the galaxy distribution to be circular, it's a good indication maybe you're looking at the cluster along the main axis along the line of sight, and therefore you might be able to correct the velocity dispersion you measure by the distribution, by the shape distribution of galaxies. But it's a project I never got time to explore. So I don't know if it would ever be done. Probably not by me. It didn't work out. Okay. So good I didn't spend time.
There is no more question. Thank you again.
Thank you very much.